introduction. Thank you for coming. Nice to see that interest. I'm happy because this room is like so far away. So I'm Alex. I want to talk about discrete global grid systems, DGGS, in a more holistic way, yeah, from the data, but then also the API, which is an OGC standard. Okay, why in an era of unprecedented data collection is it actually still fairly challenging to create vital intelligence? So question, how can digital twins be realized on the vast amount and variety of data? Also, we can ask ourselves, what are digital twins? There's different interpretations. And what are typical struggles to unlock the full potential of Earth observation data? And one of the points that I want to make is the classical way how we deal with spatial data is one of the challenges still. So one point is really areal distortions of grids. And here I'm coming a bit more from a data cube perspective, from a raster point. We can have global rasters, so we can do that. But then the pixels, the further we go to the northern or southern latitudes, the more different is the area that the value represents, right? And another thing is, even if you would have a raster in the same projection, even with the same resolution, let's say 10 meters, like Sentinel, they could still have different origins, and they would still not be perfectly aligned. They could be like, the origin could be 1 meter off, and even if it's a 10 meter, same projection raster, you would still have to resample to do some decent analysis. What if we wouldn't have to deal with that? Let's say we would assume we have something where we can put pixels that have the same area representation everywhere on the globe. Will be increasingly more important also with the climate change and the Arctic and the Antarctica changes. And if we would have a grid where we don't have to move grid cells left and right to make sure that they fit. How can we do that? With a discrete global grid system. So a discrete global grid system is a spatial reference system that uses a hierarchical tessellation of cells to partition and address the globe. So let me unpack that here for a moment. It's global, it's wrapping around the Earth, so it's equally valid all over the place. It uses a hierarchical tessellation. That means it gets chopped up, and then at the next level of resolution, it gets smaller and smaller pixels and cells. That has a mathematically reliable property. That means at any time you know the ID and the area and the location of that particular cell. So this is a fantastic thing. So we can partition because we know this piece will always be this piece and then the next one, and addressing because the IDs are unique and globally are valid. So let me introduce a little bit of terminology so that we can just get over with. So a discrete global grid is a set of zones at the same refinement level, so meaning at the same zoom level, that uniquely and completely cover the globe. Okay, that's a single global grid. Then you have a global grid hierarchy. That's basically the set of grids at the different refinement levels, right? You have really coarse grids and then finer and finer and finer, and they are related by their hierarchical subdivision. Then we need a global grid reference system, DGGRS. So I might mess up, not mess, just mix every now and then. We say DGGRS, sometimes we say DGGS. Most of the time we mean that this DGGS needs a integrated indexing system to address the discrete global grid hierarchy and the zones. Yeah, so like maybe you've heard of H3. Have you heard of H3? So H3, you have an identifier, and that identifier is well described, and only the hexagons together with that identifier make up the reference system, right? And then a global grid system, you put this all nicely together, and you have also software and libraries to actually express this system, make it useful. And then historically, we would use to call those things cells. Since the OGC standard has been more been using the word zone. Historically, grid from grid cell, grid cell. So, but then a zone identifier or cell ID when we talk about parent and child zones, we say the relationship between the different resolution refinement levels. If a child cell, we can say it's belongs to a parent at the coarser zone. Refinement level, also called resolution, is basically our zoom level. Historically used resolution, but resolution always has to be an absolute measure, right? A resolution of 10 meters, but the grid cells are more like the Mercator zoom level. So a zoom level doesn't associate immediately a direct measure. So zoom level 9 doesn't mean 9 meters, but we know internally that the 9 resolution zoom level might mean 30 meter pixel, right? And then refinement ratio, also called aperture, that is how many children zones the area together fit with a parent. So in H3, you have 7 child hexagons, the area together exactly that of a parent hexagon. And then a classic 4x4 pixel subdivision is aperture 4 or refinement level 4 because exactly subdivided into 4 pixels. Okay, I have some of the terminology. So a little bit history because this is also the academic track. It's not only a tech track. So the methods and techniques that are now the fundamentals behind discrete global grid systems, they date back to actually even more, but to the 50s and 60s. Where the first mentions in literature, hexagons used in geospatial space filling curves, like Hilbert is around 1960 something, and also hierarchical analysis methods. Then we have another period, the 1980s, 1990s, the projections used to project basically these cells onto the sphere. There we have a Snyder, typical now well-known equi-area projection, and the lattices, how we do this slicing and dicing the subdivisions. And then in the early 2000s, it became serious. Then we have a couple of papers, Goodchild, Kimmerling, White, Kevin Zarr. There the terms discrete global grids, geodesic grids, global grid systems, this is when they appear, 2003, 2005. And I want to highlight maybe 2 particular discrete global grid systems. I'm pretty sure everything around hexagons really fundamentally originates from that, from Zarr 2002. Also the tooling, DG Grid, was one of the first really researchy experimental tools that implements various of these grid systems. And then we have HEALPIGS, and that actually originated in astronomy. And instead of looking onto the sphere, there were sitting astronomers on Earth looking into the sky, having this, the sphere around them, and then say, okay, in this piece of the sky, I saw that galaxy, and then there's those stars. So this is where they came up with that type of addressing. Now, HEALPIGS is used very widely in the climate community. And I like to usually liken the comparison with the neural networks, right? And the fundamental idea of neural networks, how to model that in the computer to make some magic, was also already invented back in the 60s, but just in the last, let's say, 5-10 years, neural networks and computation are now feasible and widely used. And I think we are in a similar period now for discrete global grid systems. Okay, the talk is called Building Blocks for Digital Twins. And so I'm not presenting like one particular thing, but how I currently envision, based on talking with the community, with space agencies, geoinformatics experts, how we can do global digital twins. Like digital twins is modeling. You have to be able to simulate processes. You have to access data. You have to produce outputs, visualize outputs, something for decision-making, reaction. So the hypothesis is we can do that with discrete global grid systems, which I just introduced. And then for that, we also need some cloud native or read-optimized data sources, data formats, because we now talk about the whole Earth, right? We don't say like, okay, we have like 1 million separate raster files, but we have we have basically like a single addressable lake or, I don't know, bucket of pixels for the whole globe. As a little side discussion, which I had today, actually yesterday, maybe the step back what to do with the DGGS, because many of you will have heard of H3 and now A5 being the Pentagon, super popular. Google has doing S2 for a while. So I see two types of use cases in DGS, and mostly you will have heard spatial indexing, right? So we have our vector features, we have points, we have massive amount of points, point binning. So what we use classically for spatial indexing are things like R trees or KD trees, where we say, okay, within this bounding box, there is something, right? This is then used for spatial filtering, so I only have to check a smaller bunch of features when I have to do the actual calculations. And of course, also point binnings, counting, point counting, densities, address points, building footprints. Instead of having to use one single hot index, like in a post-GIS table, that index would have to know always all the features. You would have, like, if you have a post-GIS table with 1 million features or 1 billion features, you can only do a spatial intersect, and for that, the index has to know all the geometries in that place. If you would now want to break up this table into two tables, partitioning, big data, then this index doesn't know from that index. You could say, okay, everything from this bit is in this one, and from this bit is in this one. That would be maybe a way around. And similarly, in discrete global grid systems, if we now just take the unique identifier alphanumerically, we can say from 0 to 1 million is in this table, from 1,000,001 to 2 million is in the next table. And this is a very typical partitioning trick used in big data. And it's very readable also in tabular mindset, which is easier than geometries for many. The other bit is what I insinuated before is data cube, right? And the data cube approach for us, especially in Earth observation, as we collect a lot of data, satellites, climate models, is a pixel-based approach. Now, the problem with pixels is that they are either in lat long, then you don't have projection or unit information. You have to always calculate how large a pixel would be. Or you have a projected area where you say a pixel is 10 by 10 meters, hopefully, in the middle at least. And then top and bottom is actually slightly different width because of the latitudes, right? But you cannot really do a global thing with both. With DGGS, I'm thinking, you would have now a global single projection because all the pixels are meaningful. And you have sort of a tiling overviews, aggregations basically natively included because you have the hierarchies, because you have the parent-child relationships, you always know, can easily do summaries. And especially the data cube approach versus the spatial indexing approach, I really want to do spatial modeling, right? We need neighborhoods, we need kernels, we need globally, applicable modeling algorithms, and they run on pixel-based, right? So, just to show the example, right? Classically, when we do, for example, catchment hydrology, geomorphology, we have to decide: do we do 4 neighbors or do we do 8 neighbors, right? So the first decision you have to do when you do like a water flow accumulation. So in my preference, if we would do a global ones with hexagons, you have always 6 neighbors, right? I think this is also one of the beauties where people get quite enticed by H3. The hexagons are really nice space-filling, space-covering shape. Easy to see patterns. It's fair in all directions. They're all official direct neighbors. And you can then do nice analysis. So this is a bit of my opinionated classification now. Happy to discuss that. So we see a lot, like on LinkedIn now, I see like every second day somebody doing DGS, and then, hey, we do DGS. But then you see mostly those ones, up to here actually, because those are more well known, right? But I say those are all for indexing. Right? Most people do indexing. Okay, I have this feature, I have this data set that covers that bounding box. I have these points, so many points in that area. So we use those for indexing. But as I said, from a data queue perspective, we need pixels that have a fairly well-defined hierarchy and something where we can do something pixelish. And they have to be equal area. So here picks, I said, the astronomers, it's good. And it's diamonds. It has a couple places similar, like H3. Like all of these systems actually have one location, 12 locations, depending on their design, where they have a couple, where they don't have exact the same neighborhoods, right? But that's like literally, if you have billions and billions of cells, it's still only 12 that have a special location, and they're often on the water. So that's really should not be the drawback. And then, as I explained, aperture, refinement ratio, there is actually something that is really like H3, but it is equal area. That will be my lightning talk in the afternoon. Our HealPix comes from New Zealand. It's also quite well designed, but it has an aperture 9, so the steps between the resolutions may be too big. So resolution 4 is probably where many people are used to with pixels. The pixel 4 subdivision is maybe something good. So I'm thinking that actually there's not so many DGGSs. So when people now say, oh God, there's now so many different ones. But actually for most use cases, I think it comes down to less than a handful that are really have to be interoperable. Coming back to building blocks, okay? So we have now maybe indexing a spatial reference grid, okay? And now how to do something with that. So you know OGC standards. I mean, most of you probably have worked with WMS, since 20 years. Web feature service for features, vector data, web coverage service for raster data. OGC has now this new generation, OGC APIs. They're now JSON-based APIs, REST APIs, no XML anymore. And there's also OGC DGGS now. So literally, it's not a draft actually, it's 17th of October. It's finally officially an official standard. And this is also REST-based. And you query that with IDs, with those cell IDs. You put the data in, and it abstracts your stuff under it, and then you can say what is in this area, and you address the area via a cell, and will tell you where to find what. So there's a couple, this is the classic Swagger documentation. The semantics are basically like this. DGR SID, that would be something like H3 or IGO7 or HealPix. Then zones, and then the zone ID, which is the cell ID, and then you would get information, what do we have here? And you can also have that with collection, then you know already the layers, let's say the layers, right? Could be elevation or temperature. And then basically for that collection, with that DGGS, at that zone ID, and then you can say something like a tile, you can say depth 3, 4, 5. You can say query that, and then you get this tile with all the little pixels in there, similar like tiles. That's sort of fundamentally how this works. And this is only a standard, right? But if we put these things a little bit together in the big picture, now building blocks, let's say we have things like Parquet, cloud optimized format, Zarr. We can put them into buckets somewhere. Into some cloud storage, and then these are DGS indexed archives, so the pixels can be nicely queried based on partitioning schemes. And we can put a OGC DGS API for more this web type stuff, easy access, single small queries. But we also want to do big data compute. We want to do planetary level time series and whatnot. And there comes then in that you would just directly access the bucket. I mean, this is just, as I said, it's like a building system. And for the OGC DGS API part, we've developed pydggsapi API, sort of inspired by pygeo API or TyTyler from Development Seed. It's Python fast API. There's two basically implementation plugin systems, one for the GISs and then one for the data sources. We have also a tiles API for easy viewing. I can load this into map or QGIS. Right now we support Zarr, Parquet, and ClickHouse as data stores. It comes with the IGO7, but also H3. And Jerome St. Louis is also here, DGGAL. DGGAL is aimed to be the next GDAL, but for DGS. So he implements several GGS. So this is basically there's a configuration where you can say what's the layer, where's the data, what DGIS system is used. So it can be configured. And then, yeah. So you can go to GitHub, Landscape Geoinformatics team. And there's some notebook for interaction testing. There's some configuration examples. It's currently also tested in the OGC DGS pilot. As I said, there's a tiles API client. So nice to look at. And for the compute bit, right now we do this via Xarray, Python Xarray, and there's an XDGGS plugin that uses a one-dimensional index, not a two-dimensional or 2D time, but it's the ID of the, what's the time? It's 1 minute. I think it's looking good there. So, and then we do visualization via Longboard right now. This is a pretty good visualization library. So for the compute bit, and that would be XDGGS, and that came out of the Pangeo code sprint for the Xarray people. So they would then, this can also use the Zarr. It can load the Zarr from the bucket, and it's the same access mode the way pydggsapi API accesses those type of Zarr or Parquet ones. Yeah, so the one tricky bit is maybe that the larger the Zarr lake, let's call it, becomes, we need to be able to know still where in the chunks are which IDs. And the classic way in Zarr is that the full dimension is stored in the Zarr file, but there is now some experimentation with sort of auxiliary data that we can say ranges. For example, range indices, and immediately it becomes much smaller. We say, because the indexing is via alphanumeric, so we can sort of know which cells are existing. If it's a global data set, technically you don't need any, because you know you can calculate the order from the space-fitting curve always. So that, but most of the time we probably don't have a global data set, and then we want to know in which region we have data. Yeah, then there's also a little summary. This is just a little side gimmick of mine. If you find some information that is not in there, feel free to send something. There's all sorts of libraries and websites and stuff in there. Yeah, and that would be it. Sort of an overview of where this whole thing could go. You can have massive data amounts in the back end. You can use it with a big compute or OGC DGS API. And yeah, and smart indexing system. Thank you.
We have time for a quick question. If someone in the audience want to ask something to the presenter. Oh, yeah. Please speak in the
Okay. Thank you, Alex. My name is Rondell Pines, Texas A&M. I was wondering about how you guys deal with edge effects if you do some, calculations. So you get part of the, the cell or the zone is being cut. Do you have any functions or methods how to deal with that? Thank you.
That's were you in the workshop yesterday? No, on Monday. Oh, no, on Monday, yeah, on Monday. So I had this workshop on Monday, how to do some of that processing, pre-processing. As I said, there's these several, these two sort of approaches really. And in this approach, I would not, you don't cut pixels in half, right? Either you choose a higher resolution to better represent the area, right? Right now, the situation is obviously that we are sort of in a catch-22, right? The data is not collected in DGGS, so we would have to resample to put it into DGGS, do then our analysis. But there's project also currently going on with, for example, ESA. And that project is called Grid for Earth. And there, for example, we look into experimental methods if we would take satellite data, Sentinel-2, at level 1, before it becomes level 2 with the post-processing and the reprojecting. If that would go into a DGGS, what would be the repercussions? Would there be quality loss? What would be the most efficient, least error regridding, resampling methods to basically arrive at the same level? And then for post-production, people could still take this one back to UTM zones, and then comparing if there's a quality difference or not. And then this is currently ongoing.